Hey everyone, we're going to take a look at number 11 in section 3.10. A lot of words here. Let's read through the problem. We have a hot air balloon that's rising vertically. It's being tracked by an observer located 5 kilometers from the liftoff point for the balloon. At a certain moment, the angle between the observer's line of sight and the horizontal is pi fifths. That would be, of course, in radians, not degrees. And it is changing at a rate of 0.2 radians per minute. How fast is the balloon rising at this moment? We're told to let y be the height of the balloon in kilometers, t is the time in minutes, theta is the angle between the line of sight and the horizontal, of course, in radians again. And use decimal notation. Give your answer to 2 decimal places. So a lot of stuff going on here in this problem. They don't give you a diagram. So the first thing that I would do if I'm doing this problem is draw a diagram. And that's what I have done. So from the problem statement, you might need to read it a couple times, to get through what's happening. But we have a hot air balloon. There's my hot air balloon, and it's lifted off from the ground and is moving vertically upward, right? We're told it's rising vertically, not worried about this, no side-to-side motion. And there's an observer located 5 kilometers from the liftoff point. So I'm going to assume flat ground here so that this is a 90-degree angle. Again, that's what we're going to assume. Don't complicate things by thinking, about hills and all that other stuff like we have in East Tennessee. So flat ground, right? And so 5 kilometers, there's my little stickman observer and watching this balloon as it rises up. Okay. We're told that y is the height of the balloon. So there's what I'm calling y, from the ground to where the balloon was. And then we have this theta is the angle between the line of sight and the horizontal. So the line of sight is the sight of the observer going up to that balloon. Here's the horizontal, right? So this angle here, theta, is what we're interested in. And we're, of course, what information are we given? Well, we're told that this angle between the observer's line of sight and the horizontal is what? Changing at a rate of 0.2 radians per minute at the instant that it's pi fifths. So we're going to assume at that instant, right, that the d theta dt, that's the rate of change of theta, the angle with respect to time, right? That's 0.2 radians per minute. And it's positive because obviously as the balloon goes up, that angle is going to increase, right? That angle is going to increase. So it would be positive. And then what are we asked to find? How fast is the balloon rising at this moment? So that's going to be the rate of change of y, right? The speed of the balloon, how fast it's moving upward will be the rate of change of y with respect to time, or dy dt. So that's what we're going to find. Of course, we're going to find at the instant when theta is equal to pi over 5. But pi over, theta is not a fixed value, right? Theta is changing. As we know, it's increasing. So we don't want to let theta be pi over 5 until we get our related rates equation. So where do we get our related rates equation from? Well, we want to differentiate the equation that relates the variables of interest, and those are theta and y. And we see we have a right triangle. And so trigonometry is going to come into play here. So again, I give you that help sheet, but you should be able to find an appropriate relationship between theta and y, namely from, if you remember the SOHCAHTOA, that saying, right, that sine is the opposite of hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So those would be one of the ones we would use here. And in this case, notice here's my angle theta. The side opposite that is y. So certainly I want to use, the opposite side. So do I do sine is opposite over what? Hypotenuse. Where's the hypotenuse? It's opposite this 90-degree angle. That would be the hypotenuse. I don't know anything right now about the hypotenuse, nothing given. I could find the hypotenuse in terms of y and the distance here, because we know the relationship by the Pythagorean theorem, but we don't know it yet. So maybe sine would not be the best relationship, sine being y over, right, the hypotenuse, opposite over hypotenuse. What else do we know? Tangent is what? Opposite over adjacent. The adjacent side to our angle is 5 kilometers. And that's what I'm going to use because I think that makes things a lot easier. Tangent theta is opposite over adjacent. Opposite is y, adjacent is 5. Okay, so there's our relationship. And now what do we do for calculus? We take the derivative with respect to time. Okay, now when you do y divided by 5, think of it as 1/5 times y. Because if you're thinking about it as y divided by 5, you might be thinking, oh, I've got to use a quotient rule here. No, no quotient rule needed. It's just 1/5 times y, 1/5 being a constant multiple. So let's do this side. When I take the derivative with respect to time of 1/5 y, the 1/5 will simply come out as a constant multiple. And then we take the derivative with respect to t of y, and that's just dy dt, right? Which is what we're looking for, right? Hey, we found it, right? So we just need to solve for that here in a minute. But on this side, we do have some work to do here. I'm taking the derivative with respect to t of tangent of theta. Notice it's with respect to t, and so I've got to use the chain rule, right? Because theta is a function of time, right? Theta is changing with time. And so the inner function is theta, the outer function is tangent, right? Tangent of theta. Well, chain rule says we take the derivative of the outer function, and you need to know what the derivative of tangent is. Derivative of tangent theta is what? Secant squared theta, right? There's the derivative of the outer function. Times the derivative of the inner function. What's the derivative of theta with respect to t? Well, it's just d theta dt, right? And that's important too, because that's the rate that we know. Okay, so here's our related rates equation. Now we can plug things in, right? Now we can plug things in. All right, I'm going to clean this up a little bit. I'm going to solve for dy dt by multiplying both sides by 5. And I've swapped sides here and done that. So dy dt is 5 times secant squared theta d theta dt. Okay. And then just recall secant squared theta is 1 over cosine squared theta. And so I can now evaluate dy dt is 5. 1 divided by cosine, I want to find it when theta is pi over 5. So cosine of pi over 5, quantity squared, times d theta dt, which we're told is 0.2 radians per minute. Okay, so there's the quantity. Now just, you can use your calculator to evaluate this. I'll show you how to do that. But I would just say up top, I've got 5 times 0.2 divided by this quantity down here. But 5 times 0.2 is just 1. So really the value we're looking for is just 1 divided by cosine of pi over 5th quantity squared. So on the calculator, I would make sure that you are in radian mode, right? Not degree mode. That's important. And then I would just do 1 divided by, in parentheses, cosine pi divided by 5. And then I'm going to square that quantity. And there we have it, right? They recall that we wanted to round this to 2 decimal places up here, 2 decimal places. So the 2 decimal places, we would round that up to a 3 because the next digit is 5 or higher. So 1.53. And notice the units. The units, first of all, because we're looking at the rate of change of the height of the balloon. And remember, the height units were given in kilometers, right? And so we know the units have to be kilometers per minute. And that's going to be true if you think about the units here, because 5, right? This 5 was the kilometers right here. The 5 was in kilometers. The units of this are unitless because cosine is, again, think about cosine as the adjacent. If you think about the ratios, the adjacent side over the hypotenuse. Well, the adjacent is in kilometers, the hypotenuse is in kilometers. Kilometers by kilometers is unitless, so there's no units there. And 0.2 is radians per minute. Of course, radians are unitless measures of angle, and so it's just really per minute, kilometers per minute. So units work out. But we knew you don't even have to do that analysis. You should know that the units are kilometers per minute. Okay, that was a kind of long one, but some of these problems take a little bit of time. I hope this helps to explain how to do this problem.